All right. So what I want to do in this video is talk about matrix multiplication and explain why it works the way it works, and then we'll do a few examples. So I want to start just with two small matrices, say A and B being 2 by 2 matrices. A is 1, 3, negative 1, 2. B is a matrix 1, 4, 2, 5. So what I want to do is let's compute A times B, and then we'll also compute B times A, and we'll see what happens. So A times B, I'm just going to copy the matrices so that that'll help us multiply. So we have 1, 4, 2, 5. And then what I'm going to do in the way that we're going to multiply is I'm going to take the rows of the first matrix times the columns of the second matrix. And if you've taken Calc 3 before, if you've seen the dot product, I'm actually taking the dot product of those two. You can think of them as vectors. But really all that means is I'm going to take 1 times 1 plus 3 times 2. And that'll be my first entry in my first row, first column of the new matrix. So this is 1 times 1 plus 3 times 2. And then I'm going to do this again. Okay, so we'll do this again. Let's see if I can get rid of the highlighter here. Fancy iPad trick. So I'm going to do this again with, that's what I want. So I'm going to do this again with the first row of A and the second column of B. And that'll give me the value in the first row and second column of our product. So this will be 1 times 4 plus 3 times 5. And then we'll do this again with the bottom row of A. So we're going to get negative 1 times 1 plus 2 times 2. And then finally, in the second row and second column of our product, we'll get negative 1 times 4 plus 2 times 5. And so if we simplify this, just algebraically, we're going to end up with a 2 by 2 matrix. And this is going to be, let's see, 1 plus 6 is 7. 4 plus 15 is 19. Negative 1 plus 4 is 3. And negative 4 plus 10 is 6. Okay, so that's the product that we're going to get. That's A times B. Let's do this one more time. But now let's compute B times A. And so what I'm going to do is we're just going to swap the role of A and B. So B is the matrix 1, 4, 2, 5. A is 1, 3, negative 1, 2. So we're going to use the rows of B and the columns of A. And we'll do the same process. I'm not going to highlight this anymore. But we're going to take 1 times 4 times 1 times, so 1, 4, and then 1, negative 1. So that's going to be 1 times 1. Sorry, I misspoke before. So just to clarify, we're taking the row here, 1, 4, times 1, negative 1. So it's going to be 1 times 1 plus 4 times negative 1. So 1 times 1 plus 4 times negative 1. And then in the first row, second column, we'll take 1, 4, 3, 2. So that's going to be 1 times 1 times 3 plus 4 times 2. And then finally, we'll take 2, 5. So that row 2, 5 in B and multiply that by the columns of A. So we'll get 1, negative 1. So it's 2 times 1 plus 5 times negative 1. And 2 times 3 plus 5 times 2. And what we're going to end up with is we get the matrix negative 3, 11, negative 3, and 16. Notice that we get a different answer depending on whether we multiply A times B or B times A. So in general, this is going to be true. In general, A times B is not the same as B times A. There might be occasions where the order doesn't matter. And so there will be occasions where they are actually the same, but in general, we can assume that they're the same without any extra information, without actually computing it. So that's how we multiply matrices. That's at least how we multiply 2 by 2 matrices. And what I want to do now is I want to describe why matrix multiplication works the way it does, because it's a little bit strange if we can't see behind the curtain of what's really going on. So what I want to do is I want to consider a vector x. By a vector, again, if you're comfortable working with vectors, that's totally fine. If you're not, you can just think of a vector as a row or column matrix, depending on the situation. So in this case, I'm going to use a column matrix. So this is a 2 by 1 matrix. And so I'm going to consider a vector x. And then what I want to do is I want to consider also a function, which we're going to call an operator. And the way that this function works is it's going to have two inputs. It's going to be a function of two variables, x1 and x2. Or I can just think about it as having an input of the vector x. And what we're going to do then is the product. So when you put the vector x into this function, your output is going to be x multiplied on the left by a. And so let's say A is just the matrix A, B, C, D. And so if we were to look at that, we would end up with A, B, C, D times x1, x2. And then this definition is fine. There's only one column in the second matrix, so we're just going to take the rows of the first one, multiply that by the second. So this will give us a new vector, ax1 plus bx2 and cx1 plus dx2. And we'll talk about these types of operations much later in the course. These are going to be really important for us, and most operators that we're going to talk about are going to have a lot of properties that this operator has, but we're getting way ahead of ourselves here. So I just want to take a step back and think about this just as a function of two variables. So you input two variables. Our two variables are x1 and x2. And then your output is also going to be two variables. You can think of it as a vector with two components, I guess. So you have ax1 plus bx2, and then cx1 plus dx2, where a, b, c, and d are whatever numbers you like. So that's what this operator is going to do. And what I want to do is I want to think about, let's say we have this operator t, and let's say we also have another operator x, s. And S is going to be multiplication by the matrix B. And B will be the matrix, let's say, E, F, G, H. Okay, E, F, G, and H just being generic constants. I almost don't want to use E because it means something. I do not mean the number 2.718. I just mean generic. They're just kind of space holders, just like A, B, C, and D. Okay, so they're constants there. All right, and so what we're going to do is this will have the same process. So B times X is going to be E, F, G, H times the vector x1, x2. And this process will be the same. It's going to be EX1 plus FX2 and GX1 plus HX2. Okay. What we're going to do then is I want to think about if I were to compose the two. So if I were to take T composed with S, remember what this means is this is T of S of X. So in other words, we're going to take our matrix, whenever I take T of something, I'm going to multiply that something by the matrix ABCD. So we're going to take the matrix ABCD. We're going to multiply that by S of X, which we just found to be this EX1 plus FX2. So this is EX1 plus FX2, GX1 plus HX2. I want you to pay attention that this is a 2 by 2 matrix. ABCD is a 2 by 2 matrix. It's got two rows and two columns. EX1 plus FX2 and GX1 plus HX2 is a 2 by 1 matrix. It's got two rows and one column. Even though it's wider, it's because the terms in the matrix are just longer, so I need more space. So they're not the same size even if they look it. I just want to point that out. And the product is going to work the same way. We again have the rows that we'll use from the matrix ABCD, and then the column matrix EX1 plus FX2, GX1 plus HX2, and so on. So what we're going to do is we're going to get A times this first term. So that's EX1 plus FX2 plus B times the second term, GX1 plus HX2. And that's again going to be just a 2x1 matrix. So we're going to have 2 rows, 1 column. It's just now a really long column. So we're going to do the same with the bottom. We'll have C times EX1 plus FX2 plus D times GX1 plus HX2. Okay, so that's what that product is. And what we can do is we can think about distributing the A, B, C, and D, collecting all of our terms. And the way that I want to group this is I want to think about this in terms of x, some constant times x1 plus another constant times x2. So I'm going to write this as AE. So I'm going to look for the x1 terms. So we have AEx1 plus BGx1. And then the x2 terms, if we distribute and then collect them, will be AF plus BH x2. And then likewise for the bottom, our x1 term will be CE plus DG x1 and CF plus DH x2. So that's our matrix. And you can think about this as being a matrix times the column vector x1, x2. So if we go back, I just want to take one small step back and think about how did we compute that product? Well, we had a matrix times x1, x2. So I'm going to kind of unmultiply in that sense. And I can think of this as AE plus BG, AF plus BH, CE plus DG, CF plus DH. That's a 2x2 matrix, all times the vector x1, x2. So when I compose T and S, I end up with, it's as if I'm multiplying by this new matrix, AE plus BG, AF plus BH, and so on, right? So that's a new 2x2 matrix that we're multiplying by. I also want to think about, so just to keep this in mind, this is T of S of X. I also want to think about T of S of X in a more abstract way. S of X is where you take the matrix that we had and we called it B, and we multiplied by X. Okay, so we wrote S of X as B times X. This X, by the way, is our vector. T, the way that the operator T works, or the function T works, is you're going to take whatever the input is. In this case, it's B times X, and we're going to multiply on the left by A. So this is A times BX. It turns out matrix multiplication, this is actually a much less obvious fact than you may realize, but it turns out matrix multiplication is associative, meaning that I can write A times B times X and not have to worry about where to put the parentheses. But this is A times B times X, so I can regroup the parentheses that way. So I can think of T composed with S of X, this composition of operators or composition of functions, as a product or multiplication of matrices. Okay, that's the key insight. And what is this product, A times B? Well, it's got to be this matrix, AE plus BG, AF plus BH, because that's what A times B is. And let's just double check that this is all consistent. Remember, A was the matrix A, B, C, D. B was the matrix E, F, G, H. And A times B, if we do this, if we do this product, we're going to use the rows of A and the columns of B, and we're going to end up with, oops, there we go. We're going to end up with A times B times EG, not A times B, AB and EG. So we're going to have A times E plus BG. Get rid of the ugly parentheses here. We don't need them. So this is A times E plus BG, and AF plus BH. Okay, so in the next part, we're going to have AB times FH, and then we'll have CD times EG, and then CD times FH. And it turns out when we write this out, what we're going to get is C times E plus DG and CF plus DH. And that's exactly what we found before when we did this by thinking of this in terms of composition. That's exactly what we found before here when we're thinking about this matrix product in terms of compositions of functions. And so now it should be a little bit clearer why matrix multiplication is not commutative. It turns out it's not commutative because T composed with S is not the same as S composed with T, where S and T are operators, at least not in general. Maybe there's some particular operators where that is true, but in general, it's not true. So if we don't know any other information, we have to assume that T composed with S and S composed with T are not necessarily equal. Okay, and you can think of this fact is really easily understood if you think of just kind of generic functions. Let's say we have f of x is x squared, and e to the x is g of x, then f composed with g of x is going to be e to the x quantity squared, or e to the 2x, whereas g composed with f is going to be e to the x squared, right? So if, this should be an e. So if I were to take, say, 5 and plug it into either function, if I were to plug 5 into f composed with g, you would get e to the 10. Whereas if you were to plug it into g composed with f, you get e to the 25. Okay, so there's an example. I really just picked any two functions that you can think of, and the composition is not commutative. You can't just switch the order of a composition and expect to get the same thing all the time. All right, so that at least explains a little bit about why matrix multiplication is the way it is that it's consistent. We can think of matrices as linear operators. This is a thread that we're gonna kind of pull at all semester. So matrices are operators. By an operator, all I really mean is a function. So we can think of matrices as these functions like T and S that we had before. And what I want to do now is describe the process in general. Matrix multiplications are not always going to be defined. And so you can multiply A times B. It turns out you can do this if A is an m by n matrix and B is an n by p matrix. And so what you need is the number of columns of A and the number of rows of B to be equal. And that should make sense because you're multiplying the rows of A by the columns of B. The number of entries in each row of A is going to be the number of columns that you have. So you need n entries of A, and then likewise, you're going to have n values in any particular column of B. So you want the number of columns of A and the number of rows of B to be equal so that this product is defined. And the product is going to be another matrix that's going to be of size m times p. So what you do, and the way I think about this is, if you start with an m by n and you multiply by an m by p matrix, you're essentially just getting rid of the number of columns of A and the number of rows of B, you get an M by P matrix. So the product is determined by the number of rows of A and the number of columns of B. So let's do an example. So let's take A to be the matrix 2, 3, 1, 1, 0, 4. So this is going to be a 2 by 3 matrix. And let's take B to be a 3 by 2 matrix. So that's going to be, let's say, 2, 7, 1, 8, 2, 8. And I want to compute A times B and then B times A. And so A, like I said, is a 2 by 3 matrix. B is a 3 by 2 matrix. So if we multiply A times B, we're going to end up with a 2 by 2 matrix. And so the way that this is going to work is we're going to take the rows of A and the columns of B. So we're going to take that product just like we were doing before, 2 times 2, 3 times 1, 1 times 2, and add them all up. So this will be 2 times 2 plus 3 times 1 plus 1 times 2. And then we'll do this again for the rows of A, the first row of A, and the second column of B. Okay, so we're going to take that row of A times that column of B, and we'll end up with 2 times 7 plus 3 times 8 plus 1 times 8. All right, and then we'll do this again. We'll take the second row of A times the first column of B, so we'll get 1 times 2 plus 0 times 1 plus 4 times 2. And then finally, we'll take the second row of A and the second column of B, multiply them together in this way. We'll get 1 times 2 plus, 1 times 7 plus 0 times 8 plus 4 times 8. And then all together, we're going to end up with a product. Help me out here with the algebra. 4 plus 3 plus 2 is 9. 14 plus 32. Nobody saw this. 14 plus 32 is 46. Okay, let's destroy the evidence there. 46. This one I can do. 2 plus 0 plus 4. 2 plus 0 plus 8 is 10. And then let's see, we get 7 plus 32 is 39. All right, so that's A times B. And now let's compute also B times A. I'm going to do this in a little bit less detail here and a little bit quicker. Remember that B is a 3 by 2 matrix, A is a 2 by 3 matrix, so B times A is actually going to be a 3 by 3 matrix because we're taking a 3 by 2 and a 2 by 3. So we'll end up with a 3 by 3 matrix. So I always just like to write these down. We got 2, 7, 1, 8, 2, 8. 2, 3, 1, 1, 0, 4. And we're going to end up with a 3 by 3 matrix. So we're going to take 2, 7, and 2, 1 and multiply them. So we got 2 times 2 plus 7 times 1. And then first row B, second column of A, so it'll be 2 times 3 plus 7 times 0. And first row B, second column of A, so 2 times 1 plus 7 times 4. Barely enough room there. All right. And then we'll do the same for the other rows of B. So 1 times 8 is going to be 1 times 2 plus 8 times 1. And then 1 times 3 plus 8 times 0. And let's get that out of there. 1 times 1 plus 8 times 4. And finally, the last row B will be 2 times 2 plus 8 times 1. 2 times 3 plus 8 times 0. And 2 times 1 plus 8 times 4. All right. And so altogether, we're going to end up with, here's again where as a class I would really, really, really want your help. We've got 4 plus 7 is 11. 6, 7 times 4 is 28, plus 2 is 30. 2 plus 8 is 10. 3 plus 0 is 3. 1 plus 32 is 33. 4 plus 8 is 12. 6 plus 0 is 6. 2 plus 32 is 34. Okay. Hopefully I did the algebra correct there. All right, I don't see any glaring errors. That doesn't mean they're not there. But anyways, that's the product of B times A. That's how matrix multiplication works. I want to just hammer home one idea here. Notice that A times B and B times A are not only not equal as matrices, they're not even the same size. A times B is a 2 by 2 matrix. B times A is a 3 by 3 matrix. So it's really the case that A times B and B times A are not equal. Okay, they're not even necessarily going to be the same size. So we have to be really careful about the order that we're going to multiply matrices by. And that is an overview of